Hello friends and welcome to a lecture on numerical methods. Now this is something which is essential to all engineers and all scientists. Numerical methods are something which is, you have a lot of softwares for it. Now why does one go for numerical methods is because sometimes getting an analytical solution to any problem is time consuming and it requires a lot of skill. It requires a lot of mathematical skill. Now, an average person can use the numerical softwares, the numerical solution softwares, and he can program it to give you the answers which he really wants. So, without much delay, let's go ahead. I am Professor Arvind Prasad. So, today we are going to look into numerical solutions to ordinary differential equations. We will use the Eulers method to do it. So what is an ODE? An ordinary differential equation is not a partial differential equation. So ordinary differential of any function. Okay, an ordinary differential. So you differentiate only with respect to a single variable and you do not impose the condition that the other variables are held constant. You do not impose that condition on it. Okay, and a differential equation is as I have said already, it is with respect to one variable, and this variable with respect to which you differentiate the function is the dependent variable. Okay, so that's it. Let's have a look at some examples. So we have y, which is an independent variable, is a function phi of x, and the function is written as x square plus 1. If we differentiate it, we get dy by dx, that is differentiating with respect to x. So that would give us phi dash x, which would be 2x. Now dy by dx is equal to fx, where 2x is written as a function fx, is the differential equation. Similarly, we can write a differential equation of two variables where y is nothing but a function omega of x and y, which is equal to y square plus x cube. Now, if we differentiate it, we get omega dash x y. That is the first differential. Omega dash, whenever you write a function and you write a dash over 8, you actually say it's the first differential. Okay, so that will be equal to 2y dy by dx plus 3x square, and rearranging we get dy by dx is equal to gxy, where gxy is the function which is 3x square 1 minus 2y. Now this is the differential equation. Now this has two variables. The dependent variable of course is x here and the independent variable is y. Nevertheless, the function gxy has the dependent and the independent variables. It has both the variables. Now, why do we solve numerically? I had discussed this earlier and let's elaborate on it. With respect to differential equations, of course, some differential equations are difficult to solve analytically. You need to understand one thing, that we have differential solutions to analytical solutions to differential equations depending on the type of differential equation that we have. So there are certain types of differential equations and there are certain methods we have. Now it may happen so that in your model the resulting differential equation that you get may not be a differential equation of a certain type for which a method would be readily available to get the analytical solution. Which brings us to the second point, that arriving at analytical solution is a time-consuming method and it has no single method. And often, more often than not, that people who have studied mathematics, college level mathematics, must have realized this, that it requires, apart from knowing the methods, a good amount of skill and ingenuity to use those methods to get the solutions. Even if the method is available, sometimes you need to put different functions, you need to replace it with different functions. So that requires a fair amount of ingenuity to do it. So that also is a skill. After all, ingenuity, skill, both of them are required, and not everybody would possess this, and not everybody would have the time to actually arrive at an analytical solution, especially if we are interested in a point solution. That is the solution that we are interested in of the differential equation. The solution of a differential equation, by the way, gives you a function. So the solution of that function, we may not be interested in the analytical solution, but the solution at either a point or in a certain range of dependent variables. So we may not be interested in the entire space. And mostly in engineering problems and problems in science, you do have boundary conditions. So we are not interested in the entire space of the problem that we are looking into. Then, as of now, as on date, with the rise in computers, computing power, and programming, you have reasonably accurate solvers which can solve. They are available today, and they are free to, like Scilab is a free to use software, Python is a free to use software, and they have very good solvers inbuilt in them. So MATLAB is a very good software, but it is not a free software. You have to pay for it, you have to purchase it. It's a licensed software, as they put it. So, but yes, it does a reasonably good job. In fact, it does a splendid job. So the solutions can be plotted. Now, what can MATLAB and all these solvers do? They can plot the solutions also as graphs. And this gives you a very visual feel of the system being modeled. Now, that's a great advantage you get. Okay, so they do give you solutions at the points where you are interested, and they do take up a range from you. They ask you a range and plot the solutions visually. So it's very interesting to see visually how the system behaves to various inputs. So here we will look into one of the most basic methods, that is Eulers method. Remember one thing, this method is not very accurate, but then it is the starting point to understand many of the sophisticated methods that we have today. Is the starting point. So understanding this method opens the doorway to understand all the other higher and sophisticated methods of solving differential equations. So let's say we have dy by dx is equal to fx as a differential equation. So we can reasonably write dy by dx as delta y by delta x and equate it to fx. Now, delta y is y at x plus delta x minus yx, which is equal to delta x into fx. Now, if we take delta x as a very small value h, okay, a step size. You call this h a step size. So what do we have? We have y at x plus h is equal to y at x plus h into fx. To solve any differential equation numerically, you do have to give the boundary values. Now, they may be the initial conditions, they may be the mid conditions, or they may be the end conditions. So let's say we have, for argument's sake, we have the initial conditions, that is x0 and y0. Now, Euler's method is useful only if you have the initial values available to you. So we have the initial starting value of the function, that is the starting of the function is at x0, and the value of x0 of the function is y0. Okay, so the dependent variable is x0, its starting value is x0, and the independent variable starting value is y0. Now, they may be 0, they may be non-zeros. So what can we write now? Y x0 plus h is equal to y0 plus h into f x0. For any intermediate value of x, let us say xi, we can thus write this equation, which is written on the first line, as yi plus 1 is equal to yi plus h into f xi. Now, this is known as the Euler's explicit method. Also, there is another method which Euler has proposed, That is yi plus 1 will be equal to yi plus h into f xi plus 1. That is, we take the value of the function at xi plus 1, that is one step ahead. This is one step backward and this is one step ahead. So let's now take up a problem and understand that how do we use these methods. Now I will take up a very general way of solving this, and you can use any programming language to solve it. So let's go ahead and have a look. Okay, so there we are with a spreadsheet. So the equation that we have is dy by dx is equal to 2x plus 1. That's the differential equation. And the initial value of the function that would result from doing an analytical solution of this differential equation is at x0 we have, that is at x0 x0 is equal to 0, we have y0 as 0. Now the Eulers implicit method is written here. Yi plus 1 will be equal to yi plus h into xi. Sorry, that's the Eulers explicit method. I correct myself. It's the Eulers explicit method. Now we want to find out the value of y at x is equal to 1.3. So it's pretty simple to solve it on a spreadsheet. We put here x, we write here y, and we write here y estimated, and we write here y calculated to start with. Okay. So y estimated would be the value of y that is estimated using the Eulers method. To start with, at x is equal to 0, we have y is equal to 0. Now we take a step size here. So let's mention the step size. Now the step size is taken as 0.01. Oops. 0.01. That's it. Now, naturally, the next value of x will be equal to the previous value of x plus the step size. Now, the next subsequent value of y will be equal to the previous value of y, that is yi. So this is going to be y0 plus the step size multiplied by the value of the function. So that's going to be equal to 2 star x, that is the previous x, plus 1, and we enter. So we have the value here, and now we drag this down and see what is the progress we are getting with each subsequent iteration. And there we are. We have got the values here. Now let's have a look. If we integrate this equation, we will get x squared plus x. So what is the value initially we are going to get? Initial value is going to be 0. And the second value, of course, will be this, the whole square plus this. Enter. And let's drag it and see what is the value we get in case we calculate it. And there we are. So let's now, we wanted the value at y is equal to 1.3. So let's now drag and drop till we get the value of y is equal to y 1.3, and let's see what we get. So let's do that. Let's stop here. So we have got it to 2.2. Let's go up and 1.32. Control Shift down and delete all these values. Yeah, now let's have a look at our solution. So y is equal to 1.31. At y is equal to 1.3, The value we get from Euler's method is 2.977 and the value of the function is 2.99. Now let's see what are the errors we have. So the error is going to be ERROR, that's the relative error. Relative error is going to be equal to this. We are not going to write it down. Now this error is going to be y calculated minus the y estimated. That would be divided by the y estimated. And we would put this in brackets and multiply it with 100. So to get the relative percentage error. So that's it. Now it's 1%, and let's drag it down and see how much is the relative percentage error that we get. Now as you can see here, the error as we go ahead keeps reducing. Okay, now let's plot this function and really see what do we get. So let's plot it out and have a look at what do we really get in the plot. There we are. So that's it. So XY scatter, we want a smooth curve. So smooth, and the data ranges are in the columns. Yes, they are in the columns. And of course, data series, chart type, let us not take smooth lines only. Yes. And let's click finish. There we are. So now as you can see here, let's have a look at this chart. Now visually, if you go to see that there is a very close overlap between the estimated curve and the calculated curve. Now let's change the step size and see that really does it make a difference. Now I have taken a step size which is very, very less, that is 0.01, right? So the number of iterations from here, that is from the starting point to the end, which would be here. Okay, so we have done 130 iterations to get here. So obviously if the step size is small, the number of iterations would be less. So let's reduce the step size and see. Let's reduce it to 0.1 by a factor of 10. And as you can see here, if you reduce the step size, the error percentage goes up. And if you increase, that is if the step size is increased now. So the step size is 0.1. So it's a higher step size. Now if you reduce the step sizes, you definitely find that the error has gone down. Now step size in Euler's method, you have to remember one thing, it's a very brute method of doing it. So if the step size is low, if the step size is very low, that is you take a very small step, that is you do get accuracy which is higher. But if the step size is large, the accuracy is low. Now with this brute method, you have to do a lot of iterations to get a really reasonable value in certain cases. Okay, because now if this step size is so low, imagine if you want to have the value from a range of, let us say 1 to 10, you would have to do fantastic 10,000 number of step sizes. Now that would be really great. Now that would require a lot of computing power, and obviously it cannot be done on an Excel sheet. So that is what we need to understand one thing. This is a good method. It's not a bad method, but it is a brute force method which requires very small step sizes, which of course would require greater amount of computing power to solve the problem. Right? So this was all about the demonstration of the explicit method of solving it. Now let's take the implicit method. So we write it implicit. And let's solve the problem using implicit method. So the only difference between, and let's copy down here. The only difference between the explicit and the implicit method is in the implicit method you take it as xi plus 1. So there we are. Yes, this is the way you solve it. You take the xi plus 1. You take a forward value. So how do we do it? So let's take it here. We put here x, we put here y estimated, and then we put here y calculated, right? So the starting value is 0, y estimated starting value is 0, and of course this would be 0. Now the next step is going to be is equal to, so let's take a step size. So 0.01, a reasonably small step size. So the next value of x is going to be nothing but the previous value plus the step size. Now, yes, okay, let me do this and now the value of y will be equal to the previous value of y plus the step size into, in brackets, now this is going to be 2 star the value at this point now plus 1. That's it. And now let's do it. So let's even take the calculated value. So the calculated value, of course, is going to be nothing but x the whole square plus x, right? And let's drag it till a reasonable period. So it is only come till 0.6 here. So let's drag it till we get it to 1.3. So let's drag it double the time. So 1.24, a little more dragging, and there we are. So, oops, not to shift it. Yes, let's take this up and delete it because this is not what we want. Now, as you can see here, there is a slight amount of overestimation. So we have the step size here, and let's check out what is the error. ERROR. So relative error is now going to be defined as the calculated value minus the estimated value divided by the estimated value, and this is multiplied by 100 so that we get it in a percentage. So as we can see here, that there is an overestimation. There is an overestimation. So let's go to the end and look at, yes. So there is a slight amount of overestimation. Now let's have a look at how would the two, that is the calculated value and the estimated value, compare visually. So let's take these values and there we are. Go to chart, select your XY scatter, select smooth and select lines only and click finish. There we are done. So let's shift this to a place where you can study it well. So let's shift this now. Okay, there we are. So now let's take this. Now as you can see, there is a close estimation, but the estimation is falling short of the calculated values, but then it is fairly close. Now this brings back again the same arguments that it is good It is a good method, but it is not frequently used method. It is never used because your numerical softwares have much more better methods which could do this in fewer steps, taking reasonable step sizes, and of course not taking a lot of computing power. But of course, methods are methods, and this is the starting method, and this was the father of all the methods, you can say that. And let's see what effect does the step size have. So the step size, if we reduce the step size, let's say by a factor of 10, there it is. And we find that the errors have gone up. Okay. The step sizes have reduced, that is, the number of steps have reduced, but the errors have now gone up. And as you can see here, errors do fall, but then errors are in the order of 1%, 0.7%. So as we keep moving, of course, the errors will be there, but they will not disappear. You have to remember one thing, we are still getting an error of the order of 0.7%, which of course is, technically speaking, you would always tend to take it to 1%, you know. So if that kind of error is also not something which is what you want, then you will have to really go in for a very small step size. So let's have a demo of that. We will take it up 0, 0 and click enter. Now as we can see that the relative percentage errors are really very less, but of course to reach your answer you would require a lot of step sizes. Now you would require in the order of 100,000 step sizes. Okay, steps. So that was all about how we use the Eulers method to solve it. This was the implicit method. The former, of course, was the explicit method, and also I have demonstrated that how step size affects your calculation. So that was all about Eulers method and numerical differentiation, numerical solution to differential equations. So goodbye friends, have a great day, and do subscribe my channel. I will put the Python code for solving these at a later time, so keep watching. Goodbye.